Okay, so now we have the exact same setup. I always start these off with the word okay, don't I? It is what it is. So, okay, we're starting off with everything in our system except the Earth. So the same problem that we've been looking at one more way that we can analyze it. The more tools we have, the more abilities, the more wider variety of ways we can analyze something, the better off we are. So we're saying everything still exists. We're just now saying that the Earth is not in our system. So any energy the Earth has is not some energy that our system has. So now we do have the spring in our system again. So if the spring is in our system, the elastic energy that's present there is in our system. So I'm going to go back to this initial case. And just like in the past examples, there is still no kinetic energy and no gravitational energy because the object isn't moving, so no kinetic. The object has a height of 0, so no gravitational. The object isn't doesn't have a lot of friction, so there's no thermal energy. The spring is present. The spring is uncomfortable. It's stretched or compressed outside of its normal position, so there is elastic energy. And our spring is in our system in this example. So we again have elastic energy, just like we did before. Um, like before, now I'm gonna go switch to the final case, looking at the cart here. So when I look at the final case or position B, in this example, we've got some other things going again. Remember, the Earth is outside of our system. So if the Earth is outside of our system, there is no gravitational energy. The gravitational energy is present if the Earth and the object that or have that height difference, the gravitational energy is present if both of those things are in our system. It's stored in that interaction between the systems. But if they're not both in our system, then our system won't have that gravitational energy. So there's no thermal, again, looking at position B, just to clarify. So at position B, there is a speed there, it is moving, so there is kinetic energy. And in the previous examples, we've said that there was 2 bars of kinetic. So if we're saying there is that energy type present, I'm going to be consistent with how much energy I give it. And then at B, there is some height for the object. The object has some height above the ground. The object does have mass, but now the G of 9.8 newtons per kilogram, that's outside of our system. And if the G is outside of our system, then we don't really include that gravitational energy. So in this case, right now, we're done. That's it. So that is our final energy state. So we start off with 4 units of elastic energy. We end with only 2 units of kinetic energy. And so now when we look at position B, so gravity exists. It's just a part of this, the gravitational field exists. The Earth does push and pull on things. But the push and pull of the Earth, that effect is from something outside of our system. So when we look at this circle, it's definitely, again, not going to be an equals. And we're not adding energy to our system because remember, we end with less energy than we started. So instead of adding energy to our system, the gravitational interaction removes energy from our system. So I'm putting that arrow to go out because energy is leaving. And then I say, okay, I started with 4 units of energy. I ended with only 2 units of energy. So energy left our system from the Earth, right? So as the cart moved up here, since gravity is present and the Earth is present, just not in our system, since gravity and the Earth are present, as the car goes up, the Earth is pulling the car down. So there's a force on the car down while the car is trying to go up around that curve. So because of gravity, it slows the car down and reduces its speed, reduces its kinetic energy. So the pull down by gravity, the movement is up of the car. Those are in opposite directions. The work is negative or leaving the system with this arrow. So we know it's negative, it's going out. We started with 4, we end with 2. So the amount of energy leaving must be 2 blocks. So I'm going to take that kind of a funky diagonal. I'm going to see what I can do to fix that. Don't worry about that if you're doing this. I'm just feel like as a teacher man, I should maybe kind of get it looking reasonable. If I were you, if it comes in at a diagonal, comes in at a diagonal. We're more concerned with the blocks. But so now we're saying this arrow says that work is leaving the system. Remember, this circle is kind of like saying this is our system. The stuff that's in here is in our system, and we're saying energy leaves. 2 units of energy leave, and that unit, those 2 units of energy leave because of work done by gravity or by the Earth. We could say either one of those would be a reasonable way to go with it. I would probably say by Earth. So I hit save and close, and there we go. When I look at the equation down here, now I'm not going to put in numerical amounts right now, but I will say the elastic energy that we start off with, and then there's work done, and then that equals the kinetic energy at the end. Well, sorry, I'm kind of mixing up how I'm typing these things up, aren't I? I'll try to be consistent, change it to make it consistent with what I did on the previous ones. So I'm going to say E elastic initial. That's what I did it on the initial ones. E elastic initial, EK final, and then we have this work done by, and in this case, it's work done by the Earth and the Earth's gravitational field, and this work is negative. So I'm going to put a negative in there. I know how to make that a little plusy thingy up on top, so I'm going to do that just to kind of um, show that it's a negative value for the work. So now I've got this energy equation written out for that. I hope that helps. Have a good one.